Thank you, Matteo, and welcome to everyone to this webinar. My name is Roberto Riva, and for those of you who don't know me, I've been working in the field of reliability engineering for a number of years. Prior to that, I was working in the UK in the field of safety. And since 2006, I've been dealing with Relasoft product, first as a sole trader and more recently as a limited company. And today's case study, it's about the reliability and availability study of a power supply for a data center, for a large data center in the Milan area. 1 second, I share the... Okay. And we chose this case study because it's particularly interesting, particularly challenging as well. And there were lessons learned which can be shared to all of you. So today we'll be talking about the data center requirements. We'll be looking at the challenges that we faced and the strategy that we've adopted. Okay. Then we'll be looking not too much in details at the critical equipment because we are not power supply or generators engineers. I know there are in the audience some specific figure that are more knowledgeable than us on these topics. So we'll be looking at from our perspective, from a reliability engineering perspective. And then we'll dedicate a part to the testing that we had to undertake to demonstrate that the model we developed was sound. And we'll wrap up with lessons learned from this project, which are valuable to us and will be valuable to anybody else who embarks on a journey of the analysis of a very complex product. Okay, so who are we? And oops. Okay, as we already introduced, we are consultants in the field of reliability, and we support Relasoft product offering training, specific training on each package that we sell, but also bespoke training if there are some specific requirements. So we offer Relasoft product sales and technical support. And of course, we carry out some consultancy on specific area, in particularly in the area of accelerated testing, live data, and system analysis. Okay, so Relasoft tools. There are a range of tools. There are one whose icon is in red. And they obviously cover different aspects of reliability and product development. And we used, in particularly, product called BlockSim. That is the product for reliability and maintainability analysis. And we also use part of the analysis was carried out, or specific part of the analysis was carried out with WBS04, which is a statistical package to make some statistical, create some statistical function to be able to associate those functions to the specific model. There are also other products that we don't deal, and is the family ENCODE. There's a series of packages whose icon is in blue, but those are software dedicated to durability analysis. So, data center power supply requirements. We sort of highlighted three broad requirements: robustness of the data center. What do we mean by robustness? The power supply, as we're dealing with the power supply, must guarantee that the critical load, which are the servers, are powered even in the event of component failure. And how do we achieve that? There are two ways of guaranteeing or implementing this robustness. One is via backup, UPS and generators, and one is via multiple level of redundancy built into the design. And of course, the design incorporated both criteria. So UPS are the first line of defense against any power supply disruption, which can range from any harmonic, any unclean sinusoidal signal to a complete lack of signal, to a complete outage. And it is equipped with backup batteries, which can activate as soon as the problem arises. So that's the sort of beauty of batteries coming into function almost immediately, as soon as there is a problem. But obviously, batteries run out of power very quickly, so they provide power for a limited amount of time. And if we are lucky, we will have resolved the problem, because perhaps it's just a glitch on the line. But if we are not lucky, then we have to rely on a more stable power supply, an alternative power supply. And this is where generator comes into action. So a generator, or in this case, a diesel generator, are a relatively stable source of backup power, which can operate for as long as I got fuel, essentially. So the design had to take into account how much fuel the project was supposed to account for, and therefore that indirectly tell us how long the generator will be able to supply power. And then we got redundancy. We say there were 3 levels of redundancy built into the design. We got high voltage redundancy. The high voltage, we're talking about 132 kV with transformers and switchgear. So there was one transformer operational and one in dormant state, ready to come into operation in the event of a transformer failure. And then we have a medium voltage redundancy that comprised the ring main power distribution system. So here we are talking about a 30 kV distribution that provides power to a number of systems. We'll see there are 12 systems, and that one obviously was designed in such a way to increase the availability of the line, and therefore of the entire data center. And finally, we have the low voltage redundancy, which constitute the low voltage circuit constitute the great majority of all the equipment. And as far as the redundancy was concerned, we got diesel generator, UPS, and dual core supply to the load, i.e. to the servers. And then we have the concept of speed. We obviously try to do as much as we can to reduce the occurrence of failure, but failure will occur. Also, some of them may even be created by human being. Human being is always the weakest link in that sense. And speed, in the case of disruption, we want the power supply to activate it back up quickly, so that we don't have downtime in the system. So we want to try to minimize the downtime as much as we can. Why do we want to minimize the downtime? The answer is pretty simple. It's all down to money. And just to give you an idea of the cost, we looked into a 2016 study on the Ponemon Institute that this was done on 63 data centers in America. And they calculated the minimum downtime cost was $9,000 per minute, with peaks, if I remember correctly, something about $17,000 a minute. So we're talking about a lot of money. And when we look at the average cost of outage, we're talking about $750,000. And this is a 2016 data. It probably applies to large data centers like Facebook, like Microsoft, Google, GoDaddy.com, etc. But still, we're talking about 2016 data. Okay, challenges. What were the challenges? Well, first of all, complexity. There's no doubt about it. The biggest challenge on the project was the complexity. And so a pictorial representation of the power supply was extremely challenging. We could have probably wallpapered one of our meeting rooms with one of the drawings. And there were obviously a very large number of components. And we had to decide what to include into our models. there were 12 replicated systems feeding a large number of cabinet rows. We can show you just this picture because it's a very sort of generic picture. On the top left, we have the high voltage circuit, 132 kV down to 30. Then we got the medium voltage distribution. And then below we have two data halls represented by this dotted line, this orange dotted line, data hall X and data hall Y. Each one includes 6 systems. So A to A, B, C, D, E, F, and all the rest to L. So we have this, the majority of components were gathered into obviously these systems. And what you see here as a simple circuit breakers, in reality, there was an array of circuit breakers. What you see here as a sort of wide rectangular blocks, in reality, there are 25 load sharing blocks. So there was a lot of data, a lot of duplicated data in that sense, so there's no doubt about it. But at the same time, each system had to think independently. And we'll see that because in the event of failure, we had to act directly on the system, or we had to act on all the system, depending on where the failure occurred. So it was not possible to analyze every component. So we ran an analysis and we decided to filter it down to the roughly about 470 blocks. Okay. So as I say, there was a lot of components. This diagram, I can show you this diagram because they were not included into the system, so they're not part of the design. If you want, they were kind of a warm up to help us to say test certain configurations, see the behavior, and see if we could apply some of this configuration into our design. So if you want, they were kind of a more warm. Then model behavior. It was important to understand how the system operated under normal and credible fault condition. We didn't have knowledge of how Datacentre operates. We could sort of look at the electrical drawing and get some understanding, but one thing is to look at an electrical drawing and see, say, a continuity of the power supply. The other thing is understanding the sequence of operation. Okay. There were different operations, if you want, built into the system. We have to basically use guidance from Lombardini, who's the program manager. We have to really choose what was the most representative behavior of the data center, particularly under credible fault condition. So in other words, how would the system recover in the event of failure? And then comes the question of data. Unlike any other project we worked on, data wasn't a problem. Just couldn't believe it. You know, we had a book which contained a lot of data. And we also went outside this, if you want, traditional approach of finding data into standards for website and things like that. So we, with the internal connection that we have, we spoke to some supplier of electrical equipment, and we gained some insight that real data did exist for some of the equipment. So we could have, even if the supplier had been chosen for that project, we could have replaced the desktop style data, if you want, with some real manufacturer data. However, at the time we did the analysis, contracts had not been awarded, and therefore we had to use the data from the reference we were given. We were fortunate that the data was in the format that we could use, and not the type of data that is shown at the top right, because those type of information are not really much used to us. So where do we get the data? We source most of the data from the IEEE 493, recommended practice for design of industrial and commercial power supply. And as I say, that contained all the data for all the system, although for some of them we decided, particularly for the batteries, we decided to move away from this data source and to do our own investigation. And we'll explain later on why. We did not use AI. We did not use AI. We didn't need it. And so in that sense, as I say, it never happened before that you do have the data or the data does not represent a problem to your project. Okay, and then we have the targets. The targets, we had two targets set. A target for dual core configuration, which translates into a language that anybody can understand, is all system working. Okay, so there is no degradation of the system. And we were given an inherent availability of 99.999%. And a probability of failure at 5 years greater than 95%. And for single core configuration, kind of a degraded configuration of the system, and in our cases, we configured it as two systems, one in each data hall being out of use. We had an inherent availability greater than 99.9 or 39, and a probability of failure at 5 years greater than 70%. We didn't use actually inherent availability, because inherent availability holds on the hypothesis that your system has reached a mature state, a steady state condition. And looking at the numbers we were inputting for circuit breakers, for UPS, for transformers, isolating transformers, and so on, it was quite clear that we were going well beyond the 5 years, or certainly we wouldn't have a stable system. So we decided to use in Blockchain the mean availability, because mean availability can produce valid results even if the system is not stable. Obviously, in a situation like that, as we found, particularly for dual core configuration, we had to increase significantly the number of simulation in order to create a fault, in order to wait for a fault to occur. Okay, strategy. So the sum of components, typical of, say, a reliability prediction, was not an option. Okay, so only one defined sequence of operation would be programmed into the RBD solution, but we had to obviously be flexible to be able to design recovery that impacted a single unit or impacted a single system, if you want, those A to L systems, or impacting the whole data center. So normal operation, all systems will be configured for failure and repair distribution. So that data came from the IEEE 493. Whilst operating or idle, so we're discussing with Lombardini that will give us some indication of what was working, what was not working, under what condition. And results were measured against the target set. Okay. And then we made an extensive use of timing diagrams to identify anything that was unknown. And that was really the great part of the work. And we also had to consider line instability. So any disturbance on the line. So this was, if you want, a block that we added external to the actual power supply design. Okay. So we call it voltage sag as a line disturbance occurring upstream of the data center. And we had to find some data on it. We couldn't just plug in a box and put some numbers in. We had to find something that was applicable not only to data set, to the perturbances in the area. So we searched data and we found the area, okay, that if I'm correct, there's terminal behind it, but I may be wrong. And we looked at the data for the Milan area, and that provided useful data that relates to power disruption lasting more than 1 second. Okay, so lasting more than 1 second, unfortunately, is a bit of a question mark. How long would that last? So we were sort of given an indication from 1 second up to, say, 2 hours, which is also quite a range. Okay, and in order to be able to derive an occurrence distribution, we looked at the time window of 2020-2022. Okay, so that one provided us with the occurrence or the failure distribution of our block for our voltage sag block. But then we had to model how long would this disturbance last for. So in other words, the repair distribution. As I said, we were given sort of 1 hour, 1 second to 2 hours. So originally we plugged in a rectangular waveform or a lottery waveform. and which basically picks any number between 1 second and 2 hours. But we weren't quite happy with that because we didn't think we had the same probability of causing a disruption lasting 1 second or lasting 2 hours. We didn't think that the same probability would be applicable. So we decided to modify into a suitable exponential distribution, like the one shown, pictorial shown in the picture. With the idea that is, yes, it was very likely that you would have a short interaction or a short disturbance, but it would be more unlikely you would have a very long one. Okay, that was the criteria. And then we have failure recovery. So a series of fault injection scenarios were generated to verify the accuracy of the model. That was very important because when you're dealing with numbers so small, it's very difficult to understand whether you're on the right track or not. But at least seeing if the system is behaving correctly, then at least it gives you some comfort. Okay, so failure recovery was programmed into the blocks, and the timing diagrams were used to verify the logic and the results. Now, there's one thing about timing diagrams. Timing diagrams in Blocksim and probably in any other packages represent the last simulation that you are executing. And sometimes we come across with some results that were unexpected. So in order to be able to understand whether we were on the right track or suddenly something quite wrong with our model, we had to dig deep into the actual results of each simulation. So we had to learn a great deal of the Monte Carlo simulation in Blocksim and analyze what was happening on each simulation and how basically the results would then average out on to give you the average availability. So that was very important because in one instance, for example, where we were supposed to have a repair distribution of for a transformer, I think it was about 18 days or 28 days. It was a big transformer, the 132 kV transformer. We ended up on the last simulation, which is the one that basically you can view as a result. We ended up with results that were well beyond what we were expecting in terms of mean life. And that was when we looked into the single simulation, understood how the Monte Carlo simulation worked, then we could verify that what was projected was correct, because we did a proof of that by replacing, instead of putting in a variable model, we put in a constant repair rate at, say, 28 days, and it produces the same answer. So that was very, very, very interesting. So as I said, if we had not done this activation, and the activation probably from the numbers, it would have been very difficult to find whether things were right or wrong. Critical equipment. We singled out UPS and batteries. The role of a UPS in a power supply design is to ensure power continuity in the event of an unstable power supply. And the UPS takes that role. So under that normal operation, UPS provide power to the connected load from the mains. And UPS converts the conditioned power to the connected load while recharging the battery. So it does two things. First of all, it makes sure that you've got a very smooth supply, and at the same time, you recharge the battery in case things go wrong. And when the main distribution line goes down, do things go wrong, and the battery provides that limited assistance that may be needed to resolve the issue, or may require then a generator to come in. And there's also a bypass line that is used whenever the main and the battery are down, and is fed by a separate bypass line. However, design configuration may vary from project to project. So here we have a very simple schematic of the UPS model operation. We represented sort of the sequence in green from start to end. We got a normal operation where we go through the rectified inverter and some circuit breakers and so on, but at the same time we are recharging the battery. So this will be the normal operation of the UPS. Then we have the UPS main not working, so we feed via the batteries, and therefore we provide power via the battery. But obviously we know the battery have a limited life. And then we have the bypass in case the main or the battery are out of use or for whatever reason, and therefore we have an alternative supply via the bypass. There's also a third one down. You see the single Q3 BP, but that is just a maintenance bypass. So we didn't consider that because we did not looked into sort of maintenance aspect or preventive maintenance, that kind of stuff. And that takes us to batteries. Batteries are critical components of the power supply system since they are an immediate source of backup power. And today, the vast majority of batteries are lithium ion. In fact, batteries are, we see them with the electric vehicle, they are changing at a phenomenal speed. Even lithium ion are gradually being put aside because there's development of solid state battery, which obviously don't catch fire compared to lithium ion. But it's obviously a very bubbly field that really is moving at a phenomenal speed. And unfortunately, our data source, the IEEE 493, did not have lithium batteries. But in fact, we looked at modeling with the worst battery, but the worst battery was something like 50 years mean life, or 435,000 hours. So there are 3 types and that was the worst one, but we knew that we couldn't really use something like that. We wanted to use something more realistic. So the standard port of battery, the standard port is 3 types of battery: the gel cell seal battery, the lead acid, and the nickel cadmium, but not the lithium. Okay. So we did a little bit of search. So we went on, we found an article from vertic.com, and that estimated the life of a battery at 8-10 years. Okay. So from these numbers, we could just do some, take some pessimistic numbers, say take 8 years as the worst case, and we could derive a parameter for an exponential reliability function. But we were not happy with that either. So we thought that it was difficult to support a random failure of a battery, and we, rightly or wrongly, we assumed that a battery will degrade more rapidly, or it doesn't degrade, it doesn't sort of die randomly. So we were in need of a shape parameter for that. So we searched the internet and we finally found a shape parameter for, I think it was lithium battery, but we got the reference in the report that we compiled of 4.6. So we then formulated the hypothesis that we had a probability of failure of 99% at 10 years, and that gives us everything we needed. So we had a 4.6 beta, we had a 9.4 eta in years, and that translated with a mean life of approximately 8.6 years, which was, we were happy because it was in line with the Vertic document, and it was miles away from the reference we found. And probably this is one example, one of the data that we moved away from the data containing in this internationally recognized standards. And probably if we'd done more search on other equipment, then probably we'll find data that differ quite considerably. And if one looks at how probably you can arrive to this 150 years mean life, it's probably, it's all to do with how the MTBF is derived. And we'll see a slide at the end of the presentation. So that was our battery that we put into our block, the red one, and the other 3 are the one presented in the standard IEEE 493. So we went away with this battery and we were happy, but not fully happy, because there was another issue which we looked into, but we didn't actually implement it. So each UPS in reality is made out of 7 cabinets of batteries, each providing full power for about a minute. So we had a total of 7 minutes cover in the event of disturbances. And if we think about batteries, really failure and repair distribution of the battery in a sense is irrelevant to the data center. I think it's more recharging that is the thing that worries us more. So an additional consideration would have been the unavailability of the battery due to recharging subsequently to a discharge. Okay, so if we look at the very crude pictorial top right, we had a discharge of the battery, and then we had gradually a recharge of the battery, which obviously will take a lot longer than 1 minute to recharge. So here, that's the first timing diagram if you want. So we did some simulation with the separate circuits, and we put in a train of battery lasting 1 minute, and then we had a blue line which represented the recharge of the battery. So in this case, we were trying to model, for example, a UPS main failure that would trigger the batteries. And we also put out of use the bypass, and we put out of use, this was not a full system, we were doing some tests to just try and see if the logic was correct. And then the second issue comes in is the transformer, is the AXFMR3150 kVA. So this is the A system transformer, again coming in, and you see that the battery has finished recharging, and then you got the dotted line after the blue line, just to look at it this side. So the battery is now available, and as soon as the failure comes in, it's ready to start covering, or at least for 7 minutes. Then obviously you clearly need a generator if you're not able to recover that. So this was only a test that we did, and we didn't pursue any further. Diesel generator. The data center is equipped with a number of diesel generators to provide alternative power to the load, and the generators are expected to take approximately 40 seconds to reach nominal speed and to operate for another 30 minutes after being cleared. So we were given this number to take into account into our design. So we had to obviously make sure that the generator will come on after 40 seconds, 45 seconds, and they will stay on for another 30 minutes. And that takes us to testing, verification, validation. So a series of tests will perform to verify the logic of the RBD model and its performance in the event of credible fault condition. And to do that, we've injected fault in every part of the circuit, more or less, to see if it was behaving as we were expecting to behave. So here we got some testing example. So actually, these are not. Okay. So here we got some testing example. We got, for example, a voltage instability indicated by this red line. Okay. And because that is on the 132 lines, we have all generators A to L that spring into action. And first, they are preceded by a UPS battery. So our UPS was not a train of battery. We could have, if we had inserted that, we would have put in another 84 minus 12, 72 blocks. But it wasn't so much the problem of adding another 72 blocks. It was, there was still something not quite working with that logic. And so we basically, the battery was represented by a single battery, if you want, lasting a maximum of 7 minutes. But the generator, this diagram is actually, or this timing is not actually 7 minutes, but it's actually 40 seconds, because after 40 seconds, a generator comes in. And because the failure is upstream, it affects all the system, all generators have to come in. So in this case, you see all the generators coming in. We got this is a different testing. This is a testing, this is a failure of transformer A on system A. So transformer A is out of use. And we got the battery coming in, and then we got the generator 40 seconds later. Generator comes in 40 seconds later, and then we have a buffer 30 minutes because it was a requirement. We want to make sure that after the fault has been clear, the generator will stay on for another 40 minutes. So we put in this buffer time of 30 minutes. Same but different characteristics here. We got the UPS battery down, we got the UPS bypass goes up. In the meantime, we put out of action, we set fire to 2 cables, the AB cable. These are the medium voltage cable going from unit A to unit B. And also we set fire to cable going from unit B to unit C. So in other words, unit B is completely unpowered, okay? And it has to rely on the generator. And so we got a few things. So basically, we got a barbecue more than the data center. Now we fire everywhere, and the system is still up and running. Obviously, we have a degraded system because some of the loads down at the far end are overloading. Okay, so within the window we are considering, which is this in minutes, we don't have any failure. And here we got another scenario. We got an E transformer out of use. We got again a trigger, and the E generator comes on, and the buffer time that ensures that the generator stays on for another 30 minutes. Obviously, this is, for example, some of the equipment in the E branch. Obviously, we couldn't show. If you imagine you've got 470 plus blocks, obviously you can't represent 470 blocks on here. In particular, if you're analyzing a window of 5 years, so there's an awful lot of data. So there's a lot of searching and trying to see what's happening because the system is just so congested. Okay, and here there's another one, more or less the same. So testing was of an enormous importance. And let's look at now what we can draw in terms of from this exercise. Timing. There's not much to add apart from the timing was completely underestimated. It was far more complex than we had anticipated. And just to put the complexity in numbers, for those who are familiar with sort of block sim, we had, as I said, 470 blocks. Plus 471, 2, whatever. We had 103 maintenance groups, okay, so that gathers certain behavior. We had 23 mirror groups, some of which included 2 blocks, some of which included 3 blocks, depending on where they were positioned. We had 38 timing blocks into the system, and we had 64 trigger blocks. And to conclude, we had 50 load sharing containers. So there was an awful lot. And obviously, we wanted to make sure all this made sense and was correct. And that's why we didn't do this. That's why the activation was quite important in that sense. The logic. It is important to monitor both the logic, but also the results obtained for any discrepancy or abnormal results. And as I mentioned before, we looked at this case of the transformer, and we started seeing some, particularly from the timing diagram, looked very abnormal compared to the actual results. And so when we had to investigate every single run in the simulation, in this case we done a small number of simulations. For the graded system, we could get away with about 300, 500 simulations. For the full equipment working, we had to sometimes run even 4,000 simulations, which was quite a lot, and that required a lot of time. But as I said, yeah, it was important to monitor the number, because by that time we carried out more or less about 2 weeks of testing. We more or less had an idea of what number we would be expecting, although we're talking about a very small number, because we're talking about 4.9 or between 3 and 5.9. So you know more or less what to expect. And the moment you pick up something that doesn't sound quite right, then it's important that both the logic and the awareness you gain from the numbers will guide you to find if there are any problem in your diagram. And in a couple of occasions, we had to check all 470 blocks, every single function, every single activation, deactivation, and every single maintenance group that was called in, and so on. So it was a lot of checking to make sure that what we've done, we felt comfortable about it. Okay, troubleshooting. Errors are not always obvious, and in this case, exactly the what if analysis helped us in this sense. One thing that we found, for example, and it probably leads us to this slide, the criteria that we would normally be applied to a small scalable system did not work well in our case with a big system. So what am I trying to say with this? We set out with the idea of developing this data center into small packets that we would store into different pages. And then obviously we would have to join them at a higher level until we run into a problem. We could not get out of one page and transfer the information. I think it was the page where we had many mirror blocks, and we couldn't find a way of transferring the information. Probably it was our ability, or whatever it was. We spent 2 days trying to find a way of transferring the information. In the end, we had to take a very bold decision to develop everything into a single RBD. So imagine you've got now about 460 blocks into one RBD, and then we have another RBD with just about 10 blocks. We could achieve certain things that we couldn't have done into if we put everything together. So there were certain criteria that we had to respect. But we, as I say, the criteria that we would normally apply from a sort of very theoretical approach worked very well, but when it came to implement it in practice, we had to use a different approach. And we were quite surprised that we didn't have any crash. We didn't have any problem because we didn't know how far we could push in terms of the number of blocks. We were not able to calculate the reliability on the analytical form. It was just not able to calculate that. It took hours and hours of trying to churn the data, but it wouldn't regurgitate any numbers. So we used the simulation to get the reliability at 5 years. That wasn't a problem. But it was, as I said, we had to take a practical approach and try to differentiate the theory from the practice. And to generate results that demonstrate extremely high target require a large number of simulations. And these took time. So simulation can run for 6-7 minutes before he was able to produce some result. And if you got something wrong, you got to adjust and then re-simulate again. And the timer blocks, we also have to be careful in design to try not to overload the system. Okay, other things that we want to add and just conclude the webinar, the metrics. Okay, availability, popular among management as it satisfies the concept of summarizing everything into one dimension, but it doesn't give you a visibility of what is happening. It gives you the number, but it doesn't give you the visibility of how you get to this number. So it could be a series of small events that will give you a whole area, okay, your unreliability, sorry, that your availability or unreliability if you want, or it could be just a single event that is responsible for the whole availability results. So obviously availability just gives you the number that satisfies everyone because it's a very simple concept. But there may be cases where perhaps you're more concerned about lots of events, small events, because that creates a lot more potential error problems and so on. Or maybe other cases where you don't really want the downtime very long. And then the other thing is MTBF. So this I would like to just connect to the topic of the battery. So when we looked at this 435,000 hours, that was the worst case. So 50 years was the worst case. It's quite clear how you got to this number. So you got to this number by simply looking at a very large population of your batteries, and most of them, well, all of them basically are replaced in advance when the recharging criteria or their functionality, say, drops below what is your target. And it may happen that one battery or two batteries here and there have actually failed, okay, and those become the failed battery of a population of a huge population of batteries. But obviously that does not reflect the fact that batteries are replaced and basically there's a very little chance that the battery will fail because the battery is replaced prematurely. And obviously, once there is its inability to provide power when it's requested, is obviously more critical. So if we look at the MTBF and we take, say, for example, for the blue system, let's consider these three systems, the blue, the orange, and the green, and we take the blue system operating up to 8,000 and the orange and the green up to 18,000, we have an MTBF of the exact MTBF between the three systems. But at the same time, this MTBF does not take into account of the system, the fact that the system has been operating for different time. And the system at one point, if we're looking at the cumulative function of the three systems, the system at one point terminates to be part of the equation. And this is the concept of this we're looking at cumulative function. But if we combine these three together, we obtain the mean cumulative function, which is a much better methodology to analyze a repairable system. It's a non-parametric methodology but it's actually proved, particularly for supplier of IT equipment, something very invaluable to understand critical installation, the effect of upgrade, the effect of software upgrade, the effect of component failure, and so on. When I stated that the metrics of LTBF tend to flatten everything, and therefore not only that, but also it rests on two important assumptions: the single population failure distribution, and the exponential distribution is the only distribution applicable to them, and in other words, the system follows a renewal process. But also that failures are the inter-arrivals are independent. The systems are identically distributed and independent, and the inter-arrival generates a constant rate of occurrence that is a homogeneous Poisson process. And these assumptions are not easy to demonstrate, and most of the time they are not valid. So an alternative approach could be used not to include in the data, but more from a customer supplying data, supplying equipment to data center. And here we got the mean cumulative function that basically condenses these three systems. So sort of the advantage of, it may look like a kind of a weird graph, but it's got the advantage of, if you want a confidence band, where I can project then my independent system and see which one shoots out of the confidence band, and those are the systems that I need to conserve, I need to address. Okay, so that's, and we finished on the last metrics, which is the MTTR. So originally, almost by default, we configure our blocks on the MTTR, so mean time to repair. But then we realized that the standard is IEEE 493 also had a mean downtime. And the mean downtime was actually a more useful metrics, because in some cases we could see that a repair was taking place, for example, for 7 hours, but the downtime was only 5. And we were concerned only with the downtime of our system. We were not really concerned, say, with the cost of the repair. So we really didn't care whether it lasted 7 hours if the downtime was only 5. So we then reversed everything back to mean downtime. And so we reconfigured the system for all the mean downtime value. Okay, and I think that concludes the presentation.